Today we're going to start a very important topic, and that topic is actually is a foundation of vector calculus. Since we have limited time always and topics are so lengthy, we try our best to capture the most important part and do some practice, some problems. So what I'm going to do, I'm going to just go over that and make it very simple and practical to you. So what we're going to discuss in upcoming weeks after today, we have 2 more weeks left. We're going to talk about field. Which field? Vector field. Right. Vector field is like a cone field. Right. Vector field is like a cone field. When you go to the cone field, what you see? Bunch of cones, everywhere cones, right? Bunch of cones. Same thing in vector field, you see bunch of vectors, like these vectors, this vector, and this vector. Okay. The thing is that, first of all, why do we need the vector field? The question is that, why we need the vector field? If you remember a long time ago, we talked about physical quantity, the things that you can touch, feel, and observe. So physical quantity has two types. Physical quantities which you can observe, measure, and and feel physically. You can touch them and feel them. There is a scalars and there is a vectors. Now scalars, just like 2 plus 2, you buy 2 pounds of banana, 2 pounds of oranges. What's the total fruit you bought? 4 pounds. But vector field require direction. So if I'm asking you push any table by 10 Newton towards right, and somebody else is pushing this table 3 Newton towards left, so what is the direction? You can say, well, the magnitude is 7 Newton, but where? When this question where comes out, then you need vector field. Another example of this vector field, why do we need vector field, is that suppose you're going outside and then there's a tree and there is a palm tree and there's like maybe oak tree, right? There's a palm tree, and what's happened, suddenly the wind start blowing, and both trees, this tree is basically bowing like this way, is basically tilting this way. Palm tree is actually very flexible, it's gonna go this way, and you are observing both trees. You say, you know what, wind is blowing both trees on one side, they push it out, but can you see the winds? No, the wind cannot be seen, so it's invisible, right? It's invisible. Now what I want an imaginary, I want imagination. I want imagination lines or arrows that's basically pretend that something is happening there, and that is a vector field. So what I'm going to do, I'm going to draw these lines, these yellow lines, and then green lines, and then I can draw a vector like this along these lines. These white vector actually helping me to understand the pattern of the wind, and that is called vector field, right? So if I do bunch of them, you see I making bunch of them, definitely it's going to take bunch of time, but and then what I'm going to do, I'm going to do the same thing here, and then I can do another thing. I say, I have a bunch of vectors, then do one thing, go here, delete this line, delete this line, delete this line, delete this line, delete lines. So what has happened? Only vector left, and now I can see two vector field. I can see two vector field and I can talk about them individually. I say, you know what, I have one vector field here, and then I have another vector field here. And I can delete this. And I'm going to talk about this vector field and do all my math about field 1, field 2. And then we're gonna actually building the whole empire based on this. When I say building the whole empire, we're gonna be learning a lot of fact figures and theorems and rules about these vector field. Okay. Vector field have many different types available. Vector field can be drawn for vector field. It can be also for fluid field, like how the water and air is flowing. It can be also for electric field, like electrical lines, probably you learn in physics right now. Magnetic fields, how the magnetic lines working. We have gravitational field, how the gravity pulling us towards Earth. We have a nuclear field. We have a electron intensity field or atomic bound field. All kind of field we have available, right? So all the field can be represented by these vectors. Okay. Now I'm going to go back and connecting the dots. So I have a vector field. I'm going to talk about individual vectors. Vector field represented by vectors. So I'm going to go here and talking about a vector field f, little arrow, it means the vector, is a function that assigns a vector to each point in the some n-dimensional region, in some n-dimensional region. And what does that mean? It means vector field f, if I say f equals to 3, you say, well, what does that mean? 3, yeah, 3, I understand 3, but where? If I say 3i, the things are complete. It means if you know, this is my y, means j direction, this is my x, means I direction, that is my z, is my k direction. If I say 3i, means we're talking about something here, this direction is 3. So this I representing along the I. Same thing if I says f equals to 5j, we are good because I already told you what does that mean. It means something look like this and this direction. J means this direction. But if I writing look like this, you remember we used to write vectors like this, these parentheses. I'm going to write m, n. It means m and n means m here and n here. So this is my two-dimensional field. And what does that mean if I'm talking about m and n? Let's suppose m is, I'm just going to writing this as called like this, f equals to 3, 5. I don't have to write I and j. You can write, it's not wrong really, but you don't have to because you already have these parentheses. So I can, if I see from the top, this one is going to be look like this. One vector here for 3, one vector here for 5, right? So we have two vectors, one vector here, one vector here. So really I'm talking about a vector which is red color vector, like here, dot, 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 dot dot dot. This is my 3, this is my 5, and this vector, the one I draw, the red one, is called f. F equals to 3 comma 5. Okay, this is my 2D. That's about 3D, three-dimensional vector. I'm going to call three-dimensional vector field. Here is also vector field. Now different vector is coming, and this vector is giving like this: M and P. Pretty much same structure. I can call 3, 5, 6. This is I, this is J, this is K. Those components. And if I want to draw this in a 3D, it's going to be look like pretty much like this. If you remember, we used to do this thing in a coordinate system. Okay, these white color vectors are the component. This is my 6, that is my 3, that is my 5, and this is my F, and F equals to 3, 5, 6. Okay, is vector field. So let's do a couple of things and then we can move on to other side of the vector field. So 2D, if I say I have a vector field look like this, 0, 0, it means I have a vector like this, but this vector is not have no magnitude, so this vector look like this. So if someone asking you sketch the field, so what you're gonna do, you're gonna take a box, draw the box, say I'm gonna drawing all these field. So where this vector f, like let's suppose vector f is a wind is blowing. 0, 0 means really is not blowing anywhere. So you're gonna say, yeah, the vector field look like 0. This is the vector field. I give you another field. I'm asking you, draw the field. What you're gonna do? You're gonna just say, well, 3i, so it means vector is going, all vectors are going in I direction, right? Maybe x-axis. If I say draw this one, I'm gonna draw another field. I'm gonna put bunch of vectors. Says, yeah, this is a field look like these vectors are going upward. If I give you another field, let's suppose I give you another vector here, put different color, f equals 2, 2i, 3j, draw them. You're gonna draw this, you're gonna say this is a box for assumption. Maybe the vector is going actually this way, both x and y component, right? Okay, let's go another one. If I draw another field and give you this field, let's suppose f equals to minus x minus y, right? I don't give you number doesn't matter really. It's 2 or 3, 2 or 3 doesn't matter. You want to see this collection minus minus, so you want to do the direction because vector field is all about direction, right? Vector field is all about bracket. I'm going to make it here, make it here. And look like this vector field is both minus, so it's going to be doing this. Look like this is a scenario where I can connect this thing. An example of, if you have a kitchen sink, right? If you have a kitchen sink and there's a faucet here, and then you fill the sink with water, right? Sink the sink with water, and then put the sink, the drain plug. If you put the drain plug here and close this guy, and then when this guy is completely full with water, you just remove the plug. What's happened? All the water is rushing, coming towards this. So if you are seeing this scenario, water is going into the sink. How you explain? How do you explain? You couldn't explain. All you need is just to draw a vector field for this. So if you see everything from the top, this scenario where the water is basically going inside the drain, what you're gonna see? You're gonna see this. Okay, and that is your drain, and everything is going into the drain, right? Same thing if you have a outside, if you go to, there's a fountain, maybe some outside, you go to sprinkler system, the sprinkler system of your water on your backyard, or your garden, or your whatever the grass you have, you want to watering that sprinkler system. You have a little tap nozzle, and it's basically spraying the water. Yeah, you can see something coming out of the sprinkler system, but you couldn't quantify. You could not quantify. You don't know how far this water is going to go and drop, but you see everything from the top. If I'm asking you to draw the diagram of how this vector field looks like for the sprinkler system, it's going to be look like this. The vector is coming out like this. So inboard, outboard, and you know what, you can draw many vector you want, but I'm just drawing as much as possible. It takes a lot of time, so we just have to be understanding more than just keep drawing the vectors. If I want to write the field, I'm going to be writing like this: vector field for water sprinkler system. I can call it FW for water, and I'm going to write like this. I'm going to say X, Y, done. If you're asking, I'm going to increase the water, decrease the water. You have, let's suppose there's a tap system here, and you turn on the tap, turn off the tap, or you change the flow of water. You can change these X and Y values based on how much water you're pouring inside the sprinkler holes, and that actually explains how this looks like. Okay, so we learned about these two things, and let's jumping into another thing to talk about. So two topics we're going to talk about today is, number one is convergence or divergence, the other one is kernel. Convergence and kernel. So let me just go in those topics and make them as easy as possible and as practical as possible. Okay. So now two things going on. Number one, kernel. Number two, divergence. I'm going to say kernel and divergence. So what we learned so far today, I'm interested in two things. Number one is how much the change and the direction. So I have two things going on. Number one, I have a scalar side of the vector field, scalar side, and I have a vector side of the vector field. Like how much the vector field change and where. Two things: how much the vector field change, where. So let's talk about the curl. Curl and divergence are two things. The first one is maybe I can call divergence. This topic is going to come back to you in another way. I'm talking about general, in general. In let's suppose I'm talking about in space now. And then same thing with curl in space. And then we're going to talk about these things in surfaces, areas, specific location, like how much about a how hot is a potato, how the air inside your room try to cool down the potato, and what is the heat gain out of the potato, how does it look like. We're going to talk about like inside the room or specific areas. But now we're talking about general, in general. What is divergence? What is curl? What is divergence? Divergence means if a vector field is star for some location, how fast it expands. You know? So I'm going to say that, well, this vector field is star, how fast it expands. Like these are the circles I'm going to draw. Like let's suppose you go to a big valley and you start screaming your own name. What's happened? The person who's standing a little bit far away from you, probably they can hear. But if you go to the open air area and then start screaming your name, your voice is basically after a certain distance, so your voice is going to be disappeared, right? So divergence is there. Your voice is basically diverge and losing the strength. As you more diverge, you're losing the strength. So that's a divergence. Same thing, another one is divergence is that how fast, the example I gave you for sink, for kitchen, how fast you converge. Right? How fast you converge. It means, example is that when you remove the drain plug, how fast the water is rushing. That's a divergence. That's a convergence. But we don't call convergence divergence, we call divergence. And if the divergence is negative, it's a convergence. If divergence is positive, it's a divergence. Let's suppose you spray air freshener in your room. It's diffuse, diverge. But as soon as you spray, not everybody in the room, or not the spray is not going to expand in your room right there. It's going to take maybe a minute, maybe half minute, maybe 3 minutes, right? Same thing if you are wearing perfumes or some sort of colognes. That smell reach out to people, take a little bit time because they need to be diverge, not converge, diverge. Okay. The other thing, curl. Curl is other phenomena. Curl means how fast the field is rotating, right? So if I have a field like this, I can see how fast the field is. So this is one rotation around this point. The other rotation is this point. Right? So I'm going to say this is short. This is much faster curling. The other one is different curling. So I'm going to make another line. I'm going to make another line. These are the curl. How fast the field is, rotational. It means another example is I gave you for kitchen sink here. Example I gave you. Maybe we can draw just for, and the water is rushing to the drain plug, and then water is coming here. This is divergence example. This example is that maybe you have like a container where you are mixing some fluid, maybe your coffee. You're putting your coffee in a coffee mug and putting a spoon here, right? And you start mixing the coffee and sugar. What's happening when you try to mix this? If you see from the top, what you're gonna see? You're gonna see these white lines, right? Coffee is mixing. Same thing if you go inside the washer and dryer. If you have a washer from top loader, it's a curve, right? It's a curve. Now I'm going to do two things. I'm going to say is what is divergence, what is curl. If you remember long time ago, we talked about a phenomena called gradient. Gradient is this. It means how much things or how much function is changing in x-axis, y-axis, z-axis. I'm going to use that phenomena today to cover this topic. So if I'm writing this gradient like this, if I write this f, it means I'm writing like this. This is my vector field, by the way. I just told you what is f. F is my vector. F equals to whatever, x, y, z, or m, n, p, q, r, s. Maybe call m and p. So you're gonna write f with f plus f divided by y plus f divided by z. Now, I'm going to take into a little bit different strategy. How can I multiply the two so it can give me the divergence or it can give me the curl? Okay, so let's talk about the curl first. Curl is a vector, right? Curl is a vector field. It means how fast the vector is turning. So you still need a vector. Divergence means how much you change. So when you talk about another word, the answer of a curl is a vector. The answer for divergence is scalar. It means you spray, reach out to me. You spray, I know where your location. You spray the air freshener. I'm sitting in a room. I smell the spray. The spray reach out to me. How fast it takes, or how much I can smell, or how much I can feel the field. That's all I need to know. I already know the direction. Vector field is different. You mixing the coffee, how fast? You washing the clothes, how fast? If you try to wash your clothes really fast, what's going to happen? They tear down and rip off your clothes. So sometime intensity important, sometime direction important. Vector field is more like a direction and intensity both. The magnitude and direction both. This is a vector field called curl. The divergence is only magnitude important. I don't care about where. I only want to know how much. Okay. So let me just talk about curl now. This gradient and f. So if I want to see curl, can you tell me or calculate the curl of a vector f? So some vector field, maybe this is a field of how fast the washing machine in your home washing clothes. Everybody have a different kind of models. Everybody have a different kind of machine sizes. Everybody putting different kind of clothes and level of water. So when you're washing clothes, everybody have a different kind of field inside the washer, right? If you have a top loader washer, if you have a side loader washer, pretty much same. It basically a little bit different direction, but it's the same thing. So I want to do the curl. I can do this. I'm going to take the cross product between this times this. If you remember, the cross product is the multiplication of two vector when the answer is also a vector. And how do we take it? We use this method. Ij, okay? And my gradient vector is all I already told you. This is this. And my f vector is m and p or prq. So I'm going to call m and when I solve this, it's going to look like, you know, this y dp or dp or dy. I'm going to do the I minus dn over dc, that is my I component, then minus from the formula dp over dx minus dn over dc, this is my j component, plus delta n over delta x minus delta m, this is n, or delta y, this is my k component. Okay, done. Same thing, my divergence is nothing but, my divergence is my dot product, right? My divergence is my dot product. So if I want to write the divergence, it's going to be dot product. I'm going to say divergence is going to be look like d, I write this df, and I just want to know how much the air freshener you spray reach out to me, or somebody talking, how fast the voice is dispersing or diffusing into the air. So I've said divergence equals to nothing but pretty much same thing. The only operator is this dot, and when you multiply, you doesn't do anything, you just stays m plus n plus, if it's a 3D you can do, and this may be m and p. Okay, so I have to this guy, and then I have this guy. Let's do examples, maybe one of each we can do it. It's very simple. We need to find the divergence. And the curl. Okay, if there is no curl, let me just go here. If let's suppose you calculate curl, your answer comes to be 0. It means what? If you solve this thing, this vector, and then answer comes out to be 0i plus 0j plus 0k. Remember, I just draw this thing in the beginning of the lecture. I draw this field 0 dot 0, and it's going to be look like just starts. No vector. I mean, this vector could be this way or this way or this way, but there is nothing. It's just dot dot dot, means vector is not even moving. So it means your washing machine is basically turn off. Nobody using the washing machine, nobody washing the clothes, and the water is stationary. Okay, same thing if the divergence came 0, it means let's suppose I'm waiting to monitor my voice, but I'm not even talking. I stay quiet. Everybody waiting, I'm going to speak so they can test my voice, but my voice I'm not even speaking, so everything is 0. It means divergence is 0. Okay, same thing if you have a sink, the drain plug is on, the sink is full of water, but the drain plug is on. It means water is not going to drain, so there is no divergence or convergence field going to create. But as soon as you pull the plug, then it's going to be drain the water. So these are the phenomena of those field. So let's do example for curl. Right, for a curl, find curl f of the vector field, and the vector field is giving something look like this. And I'm going to say, you know what, it's a function of And the question is that, is it's a passive question, is f rotational? Is f rotational or no? We need to figure it out. How we can figure it out? We can figure it out by calculating the curl. So the curl of f, usually we just write curl of f equals to this gradient times f x y c. This one is equals to, we already talked about that, I j k. I'm going to writing my gradient first. It's very important that we make sure this gradient first. You cannot write like this. It's not gonna be same. Remember, cross product is not gonna be same. It give you opposite answer, so you cannot do that. When you do the cross product, means it's important which vector came first, which vector came second. And I'm going to writing the variable this for x, y, z. So 2xy x squared plus y squared, sorry, not y squared, z squared. Z squared plus 2yc plus. And you're going to solve this. It's going to be, I'm going to take the derivative directly. So when I do the I, I'm going to multiply this to this, take the derivative, partial derivative of this to minus this to that, and writing. When I do the j, I'm going to take this to this, minus this to this. When I do the k, I'm going to ignore these two lines and I'm going to multiply this to this. So take the partial derivative and then minus this to this. So I'm going to be writing 2z. Then I take the derivative of this, so it's going to be 2z with respect to y minus 2z I minus 0 times 0 j. I take this one to this, nothing common, 0. Here I take the z, the no z quantity, everything should be 0, plus 2x minus 2x k. How? Because I take this guy jk. So if I take the partial derivative with respect to x, it's going to be just 2x minus, when I take it here, it's going to be 2y. So everything is done. This guy is 0, this guy is 0, this guy is 0. My answer is 0. So I'm going to say here, is that f is rotational? My answer is here, because curl of f equals to 0 means f is irrotational. Irrotational means not rotating. Okay. Let's move on to one example for divergence. Find the divergence at 2, 1, minus 1. This is a point for a vector field. F I'm going to say x squared x cubed is going to be x cubed y squared zi plus x squared zj plus x squared yk. You notice one thing, I gave the thing as a point like this. It means I have field is going like this. So this is a source. I can call maybe somebody speaking here is a source, and voice is, voice is getting outside and then expanding. Our voices expand, that's why people can hear, and we need air. If you learn in physics about sound, okay, I want to know my voice is expanding. I know my voice is expanding from here to there, is going getting weaker and weaker, but getting larger and larger. The domain is keep changing, larger, be getting bigger and bigger. So this is one domain, another domain, another domain, another domain. Those lines I'm just making. Okay? This point means I'm gonna finding the point P, and I need to find out from here to here how much my voice change at this point. That is my divergence. That is my divergence. I'm gonna do solution. I'm gonna write my div f x y z n equals to, it's pretty simple, we already talked about that. I'm going to take the divergence of f, so really is a partial derivative dot product between two. Let me just write here for now, for the first time we're going to write here this dot f, and this one is equal to partial derivative of which come from the gradient, and x cube y squared z plus that came from the gradient, and this is came from vector f. Then again the last part is partial derivative with respect to z came from f and gradient. Let's do. This answer will be 3 x squared y squared z plus their answer should be 0 because no term for y plus no term of z, 0. So 3 x squared y squared z. I'm going to say this d I v f divergence of f at this point equal to 3. That is my, by the way, this is my, I can also write like this. I can also write like this. This is my divergence of f. So this is the value. I'm going to substitute the points, the coordinates given. The answer is -12. So look like from the source, this divergence is basically convergence, is going towards, is getting reduced or intensify based on the sign. So the divergence is this. All you have to do, just my answer. Okay, done. You see here the direction really does not even being discussed. The answer is this. Yeah, there's another way. If the field, if I don't give you the point, you gave me this, right? If I don't give you the point, like let's suppose I don't give you the point, what you're gonna give me? You're gonna give me this. Your answer is end here. But again, this is only a magnitude because this x, y, z does not telling you where. It's just telling you the equation. In the C, we can see the vectors going up and down. So all I can do is just take a look on this, and in C we have number 6, I believe, look like the correct answer. So you can go up. If you put the x value is 6, so you're going to be 6i, and so sorry 6j, and then if you have a value of -6, you're going to say it's -6j, so it's going to be going down, right? So only one direction is giving. There is no, the field is basically unidirectional, and which is a y direction. I'm just trying to see. Okay, the part D, so the correct answer is 6 for this. The equation or graph D is look like pretty much what do we have in C. So the correct answer for D should be only one left over, which is 5. Okay, and you can see here in 5 the vector can be just go this way or that way based on our I value. So if you say 7i means 7i means this way, if you say minus 7i it means backward. Okay, okay, after that we were talking about curl. So take a look on these equations when these vectors are following any kind of circular motion, and we need to find out if there is any curl or how much is a curl. Okay, so let's go to the some more problems. So if I have an equation is given for the function x y z I plus x y z j plus x y z k, and these are the function, right? So look like we have a function which have all the three values of multiplier, so it's going to be a little bit a symmetric vector which can be circulated, and I need to find the curl at this point. First thing first, I don't even know how the curl field looks like, so I can substitute this vector or the point into that. In order to find the curl, we write like this usually, and it means this guy means really is a cross product of this. This one is and this f is basically the one which is given. So what I'm going to do, I'm going to be writing this, and I'm going to be writing like this, then I, j, k, and I'm going to be writing the first is very important that we should write in this first. So I'm going to be writing this, and then writing the component for my current vector. So I should be fx, fy, fz. Here fx is okay, look like all similar, so I'm going to be just writing here, and then when I do this determinant, finding the determinant, I'm going to multiply this to that when I do I. So I'm going to do I first, so I'm going to multiply this to that, so d over dy with x, y, z, the answer would be xz minus the derivative of d over dy for x, y, z, the answer would be xz. Plus I'm going to do the y, so I'm going to take the derivative of d over dx with x, y, z, the answer would be yz, and then take the minus the derivative of d over dy for x, y, z, the answer would be xy, and this would be j. Then plus my there's one mistake, I think I should be doing this one should be minus, and the last one would be yz minus xz, and that would be k. Okay, so I know everything here. I'm going to just say curl f, and I'm going to substitute the value for 2, 1, 3. If I substitute, it's going to be 6 minus 2i minus 3 minus 2j. 3 minus 2j plus 3 minus 6k. Let's simplify it further. It's going to be 4i minus j minus 3k. Since this is a three-dimensional field and this is our answer, you can imagine if I have a vector supposed to be look like, three-dimensional look like this, and maybe the vector is circulating maybe this way, maybe it's going to be going this way. We never know which way this field is really making. The bottom line is that I know one thing is that in this field, whatever field is that, I don't know which direction is that, but the point I'm substituting here, whatever point is, this point, the little tiny vector is that this vector is 4i minus j minus 3k. Okay, and if you substitute another vector, let's suppose you say I'm gonna be checking this one, 1 3 9. That might be the point of this vector should be other way. Remember, when you have a curl, if one vector is this way, if you change the point, the vector direction should be changing. It's always changing. So this is a 2D, even the 3D is a very unlikely that two vectors will be going to be in the same direction. With possibility, let's suppose you are making a vector field which is look like this. So you pick one point which is look like this, then you pick another point which is pretty much on the bottom here, is also pretty much on the same direction, because like a spiral field. But again, both of these vectors have the z difference. Yeah, so these are the things we have to keep in mind. Let's take a look another example for the curve. The problem is given is field is given is again 3D, x squared z I minus 2x z j plus y z k, and the point is 2 minus 1 3. If I take the curl for f, it should be giving the determinant, and emphasize more and more that we should be writing this guy first, and that's a cross product. So we should be writing this, and it's going to be this d over dx, d over dy, d over dz, or d delta x, delta y, delta z. And then we're going to be substituting the component, so it's going to be x squared z minus 2x z yz. Okay, let's take the determinant is going to be z plus 2x I minus 0 minus x squared plus minus 2z minus 0k, and there should be an I here. Okay, let's simplify a little bit before we substitute the coordinates. Okay, and let's substitute the value of this curl f 2 minus 1 3. So if I substitute, it's going to be 3 and then 2 7i, 3 and 4 7i plus 2 times to the 4j, and then minus 6k. That is my answer.
We also talk about curl as well as divergence. Curl is nothing but is the tendency of a vector field to be rotate. Divergence is basically a scalar product, right? So vector field is that um, simple is that. Let's suppose somebody somebody calling your name, that is a source of sound, and that is a reception. Like maybe your ears here is listening the sound, and somebody making a sound at this point, and then voice is basically propagating. Voice actually propagating in every direction. I just you want to know just what's happened to the voice is passing from your ear. So the source is S and reception point is P. There is two things about this. Is first thing first is how much sound or what is the volume of the sound, and what is the source direction. So two things is that how much you receive. Maybe you can say 30 decibel, right? 30 decibel is a unit of sound. So 30 decibel. The second question is that where is coming from? It's coming from this direction. So same thing when you're talking about this direction, or let's suppose you say at this point you get the 30 decibel, tell me the direction. So you're going to take the p coordinate, like whatever, 2 3 4. You're going to take this one and substitute into the curl, then give you the magnitude, and also give you the direction if it's a circulation field. But let's suppose if you're just interested in the magnitude, you don't care about where it's coming from. Pretty much for sound, usually when you talk about sound, you don't care about where it's coming from. You care about how much you got. Because if the sound is very low, you don't understand. And if you understand, that's all you need to know. What somebody just saying. And other than that, you're not interested in anything else. So that attribute of physical quantity which you only interested in is scalar part. You're using divergence. Okay. Same thing. There is a two more thing going on here. Number one is how much sound this P actually getting in, and how much sound of this source actually getting out. So if I'm making two circles around point P and around point S, we want to know that what's happened at the surface of this S. What's happened? The sound actually going out, or at P the sound actually getting in. So divergence have plus and minus. When it's going out, you call it plus. When you're going into the system, you call them minus. Or really you can call diverge and converge. Right? Converge means shrinking, consolidations, stuff like that. So let's take a look at examples of how we're going to solve divergence convergence problem. So I have a field is given. Now in this field actually, I just want to know if this is a vector. Yes, it's a vector. It's given in the component form. Yes. So you know it has some direction. Yeah. Now I told you magnitude can be a numeric form, or magnitude can be in some. First of all, it's going to be a magnitude, and or it could be a variable form. So it's going to be an equation where you can substitute the value, you can get the answer. Okay, when I say equation, it means non-vector. It's not a vector. Let's take a look into this, and then we can do maybe problem where we can find a particular value of the divergence. So here I can do just divergence. Some book says capital D, Some books say small letter key, it's not a big deal. And all you can do is just taking a dot product between this and F. When you say dot product, really you're writing like this and their component, okay, plus the dot product of dy, the y component of this, and the y component of the vector, which is 2y squared. Then you're taking the partial derivative is going to be 2x plus 4y. Remember, I just told you a few minutes ago, when you get the vector, it could be either way. It could be magnitude, it could be equation. You can see in equation form. So it's not a vector. If I give you an x in value, you substitute, you're going to get one numeric number. And this guy you can call, this is divergence. Okay. Now look a value where divergence is being have a value for numeric or magnitude is given in a numeric form. So we should have a point. For example, we need to find the divergence of f if f is giving like this. Three y z square. Okay. Let's take the divergence at this point, and sorry, the point is given. Some point is giving the point at this point. Okay, we need to go and then find out the divergence. The divergence of f is nothing but is a dot product between the two. So I'm going to take the dot product. So I'm going to take directly for this one. Maybe I can write this. Okay. If I take the derivative, is going to be y c plus 0 plus 6y c. So I need to find divergence f at this point. So I'm going to substitute 4 and then plus 24, so it's going to be 28. Okay. Now I'm going to be talking about a new concept. The concept is conservation of vector field. Okay, or conservative vector field. In this concept, really what we have here is, if we have a vector field is given, but before we do any vector field phenomena, what is a conservation means? Conservation means is, for example, if we have a, if we have any building, and let's suppose this building we want to grab some furniture or maybe a chair. You have a chair, you want to grab this chair, and then you want to put into 4th floor. You want to move it here, you want to put it here. This chair, you want to put it here. Now you have a bunch of different ways. The first option is that you can move this chair to grab it and maybe throw out ropes, and then you can pull this chair up. You put some sort of work, maybe 10 joules of work. The other option is that you can grab this chair, you can go to the stairs, then walk here, then go to the stairs, then walk here, then go to the stairs, then walk here. You get it here. If you follow this path, again, you're going to be following 10 joule, right? The only thing is that it's just more work you have to do rather than this way. So the bottom line is that sometimes you cannot reduce the efforts by changing the direction. Okay, so if the vector field is conserved, means the work done is independent to path. Independent to path. Following. What does that mean? It means if you conserve, regardless of whichever you go, eventually you're going to be get to the same efforts or same work need to be done to move around. And that's actually a phenomenon called conservation of vector field. In order to do that, we have a test. We have a test if the field is conservative or not. Let's talk about the test. Okay, and the test is let M and N have a continuous first partial derivative on an open disk so there is a disk is given, right, and the disk region is R, and M and N basically continuous first partial derivative of a function of this, the vector. Is going to be conservative if and only if so really if I put this thing in a practical prospect, it means if I have a function giving look like this function is giving, so this function actually have M component and N component. M and N means M is my X component, N is my Y component, right? So if the vector field is giving something look like 3i plus 7j, right? This is my M, this is my N. So you're going to take the partial derivative of Y component with respect to X and X component with respect to Y. You can see M with respect to Y, N with respect to X. So whatever component we have, you're going to take the partial derivative with respect to the other component, and if they are equal, it means they are conservative. If they are not equal, it means they are not conservative. It means really what does that mean in real life is the only way I'm conservative is if I'm going this way and this way, and the angle between the two is 45. I'm going this way. So regardless of whatever the field is, we have this like this. But if you have these two things are not equal, let's suppose if I'm going this way, my this component and this component never be same. It means they're never canceling out each other and give me the same answer. It means if I try to canceling out this, I always have my motion is basically going up more than going this way. So I'm always going up more than this way. It means I'm on one directional flow, right? One directional flow means if I try to do some work, it might path dependent. I cannot say my work is path independent. Let's take a look in this example, figure it out if we are conservative or not. Determine whether the vector field given by is conservative. Okay, and the field is given like this. So let's do this one. In this we need to be find out this test, conservative field test. That is my M, that is my N. So I'm going to take my M and take the derivative with respect to Y. And my M is x squared y, and I'm going to take my N, which is my second component, and take the derivative with respect to x. So the answer is x squared. This answer is y. Okay, means so if you want to draw this field, if you draw this field, something like maybe vector is going to be going this way or something. I don't know which way is going to be going. Look like it's 2D field. So in this field, if you want to go from point A to point B, yeah, there's a bunch of ways. If you go this way, it's different. If you're gonna go this way, it's different. If you're gonna go this way, it's different. Whatever way you follow is different. But take a look into another example. Check this field. And the field is giving 2xy plus 2xi plus yj. Let's do the test. And this test says this should be equal to this. When I do this test, it's going to look like when I do this, the answer will be 0, the answer will be 0. Field F is conservative. It means if I have a field like this, 2x plus y, whatever way, this field is this. So really what does that mean? If I want to go from point A to B, it doesn't matter which way I'm going to go. I have to do same amount of work, just like the example I gave you. So question is that, does the gravitational field is conservative? Yes, it does. It's conservative, right? But you can think about it. The gravitational field is conservative if you are not moving too far from Earth. is very important. It's the size of the field and the domain of the field. So if the vector field is, the domain is super big, maybe is not conservative outside. For example, this is Earth. This Earth is really big planet as compared to where we live. We just live, our atmosphere is like this, all the cloud and maybe a little further down. So if we are moving from here and there inside this field, yeah, it's conservative. But if I want to go from here to there, let's suppose you want to go from here to, to moon, then you're going certainly very high to Earth. And then maybe the Earth is not, the gravitational field is not conservative if you go further high, because the travel is very high as compared to the size of the Earth. So yeah, Earth magnetic gravitational field is very conservative near the surface of Earth, but may not be true if you're going further high, very high. Okay. Now take a look on this problem. Vector field is giving 5y cube plus 10xy squared j. Let's test this. Okay, so if I do this, the answer would be 15 y square, and the answer would be here is 10 y square, and they are not conservative. Okay, anyway.
Thank you for watching Knowledge Academy. Thank you for watching Knowledge Academy. Please subscribe my channel.